Hello, my name is Connor Stone, and welcome back to the AstroPhot tutorial series. Today we're going to be talking about PSF model basics. These are going to be the core point spread function features that you're likely to use when you're doing your image analysis. There are some more advanced features that AstroPhot has access to, but those will be covered in a later tutorial on advanced PSF modeling. For today, we're going to focus on the stuff that almost certainly everyone who does image modeling is going to take advantage of. As always, let's start by loading in AstroPhot and NumPy, Matplotlib, that sort of stuff. And then let's get right into the basics of PSF images. So again, AstroPhot is an object-oriented code, so it has a PSF image object, kind of like the target image or the model image that we've encountered a bunch before. The PSF image is intended specifically for holding on to point spread function models or images that represent the model of the point spread function. There's a few key things to keep in mind about a PSF image. First, they should have an odd shape. For example, 25 by 25 pixels, not 24 by 24. This is because, by definition, in AstroPhot, the center of the PSF model, essentially where the delta function, that is the point in point spread function, where that delta function is, should be the center of the center pixel, which if you have an odd shape, that's really well defined. It's just that middle pixel. If you have an even shape, then you've got to make some decision about which pixel or some place in between the pixels is going to be where the delta function is. And for the sake of simplicity and reliability, AstroPhot just requires that you have an odd shape for your PSF. Another thing to keep in mind is that in a PSF image, you can think of each pixel not as sampling some brightness value at the center of the pixel, but that it is actually already an integral of the light inside that pixel. Okay, so let's make our first PSF image. Here we go. So all we've done is create a Gaussian blob and added some noise onto it. And then we put it inside a PSF image object. So this is what you're going to use to store your PSFs in AstroPhot. Now, we've for the data, we've put in this Gaussian plus noise that we added in, and then we set upsample equals to 1. We'll get into upsampling in a little bit, but the main idea is that it's pretty easy to just store the PSF image like this. Some more things to keep in mind about the PSF image is that they are fully defined on the pixel scale, pixels of your image. So if you've got distorted pixels or sheared pixels, or if the pixels in your detector are odd, then the PSF image is in that space of the pixels rather than being some projection on the sky that then gets integrated into the pixels, which is what most AstroPhot models are. They're represented on the tangent plane, this like perfect linear plane that's tangent to the sphere of the sky. And then your pixels are just roughly often squares that you put on that part of the sky and try and integrate the light inside them. Instead, PSF images are right in the pixel space of your images, and that's because that's the natural place to define them. The PSF is a distortion that occurs through the optics of maybe atmosphere, definitely the telescope itself, and in the registration of the like CCDs and how they collect light. So it really only makes sense to talk about them at the level of the pixels themselves. Now, usually you want your PSF, the sum of all the pixels in your PSF to add to 1. So you can do that yourself, but AstroPhot includes just a quick function you can call on any PSF that I suggest you just call anyway, because it won't really change anything if you've got it normalized. But this normalization will just take the sum of your pixels and divide your PSF model by that so that it guarantees that the sum equals 1. And that's just a nice thing to make sure that you've got. Here we plot the PSF, and you see we have a specific PSF image plotting function. And so it shows us the pixels, the I and the J axis in pixel units. And there's our PSF model. This is like an empirical PSF. You could imagine finding a star in your image, grabbing a little cutout around that star, and there you go. You've got your PSF model ready to go here. Um, okay, so that's how you get a PSF from some matrix, maybe a NumPy, a 2D array, into something that AstroPhot is going to understand. Now, let's talk about uh, when you want to model something in the image using this PSF model. The simplest case is you want to model something in the image that is itself a delta function. So you've got some model of what a delta function should look like in an image, and now you want to model something that you think is a delta function in your image. This is the most straightforward translation between the two, and this applies for all sorts of cases, stars, supernovae. If you've got a really, really far away galaxy, maybe that looks like a point in your pixels. A quasar, often modeled as a point source, asteroids, all of these things almost certainly show up as if they're a point source in your image. Essentially, they are so small in angular size that for the sake of the size scale of your pixels, you can assume that they are a delta function, an infinitely small point of light. Keep in mind, though, that something that's just a little bit smaller than the size of your pixels is probably actually still considered an extended object from the sake of modeling perspective, because if it's just a little smaller than your pixels, then there is actually some information in how that light is distributed within the pixel that can leak into the actual flux values that you measure. It's pretty wild, but images are very sensitive and you can get that kind of information out. So anyway, let's stick to the delta function here. That's a point model. We've talked about that already a little bit in the model zoo, but we're going to really focus on it today. So the point model, the model element of it tells you that it's going to represent something on the tangent plane of the sky. This is no longer some model of what's happening inside the pixels of our detector. We are now talking about something on the sky, which means that it has to have a position and it has to have a flux. I mean, it's a point source, it's a delta function. It's pretty much entirely defined by where it is and how bright it is. Um, but then how that point source, that delta function, gets mapped into our image, of course, we need our PSF model to do that mapping. Otherwise, we would just basically be picking one pixel in our image and making it really bright, which doesn't make much sense. So here we're going to tell it, here's the PSF model that you're going to use. It's that empirical PSF that we figured out before. You initialize that point source model, so it'll make sure that all the parameters are ready to go, which in this case they already are. And now let's plot the model image. Let's see what this point source looks like. And of course, it looks exactly like our um, point spread function model, except now it's in a tangent plane. Notice that the x and y axis units are in arcseconds now. So this has a physical scale on the sky rather than being the abstract pixel units that the PSF model was in. And we can move things around. Let's make this 25 and then boom. Now it's over on the side here. So the PSF model itself is an abstract thing that's sort of like is a feature of the pixels of your image, whereas the point source model is something on the sky. It can move around, it can get brighter and dimmer. And if you then take this model that you've got here, this point source model, you give it an image to look at, a target that isn't just the dummy target we created. This target just has zeros in it, so there's nothing to fit here. But if you give it a real target of, say, a cutout of a different star, then AstroPhot can run the optimization to figure out what is the most appropriate center and flux values to match up those two. Now, keep in mind that the PSF or the point source model is now essentially reintegrating those pixels from the PSF model into the pixels of the image where you're doing your modeling. So chances are your point source model, your delta function here, this point model, is not located right at the center of a pixel. And so the PSF doesn't just get like it doesn't just get placed, stamped into your image. There's actually an integration step where AstroPhot has to take pixels the pixels that the point model is trying to represent, and it's going to sample a bunch of values in those pixels. And the thing that it's going to be sampling is the PSF model up here. Now, AstroPhot just uses bilinear interpolation of your pixel values from your PSF model when it's projecting into an astronomical image. Bilinear interpolation is not the most robust interpolation method ever, but it is very fast. And so it's suggested that if you're worried about the interpolation effects not quite smoothly representing your PSF model the way it should, say your PSF model or your PSF is not very well sampled, then the suggested thing to do in AstroPhot is to model your PSF at a higher resolution. Do an upsampled PSF. You could even use a detailed upsampler like Lanczos interpolation to really finely upsample your PSF. But then for the modeling stage where you're trying to very quickly explore parameter space, the bilinear interpolation will be very fast. We'll talk about upsampling at the end of this tutorial. But let's move on to the next case that you're going to do your PSF, the next case that your PSF model is going to apply to. So we considered a delta function, which basically just remaps the PSF into the images with a little bit of integration effects. But the story gets more complicated when you have an extended model. So let's go back to our classic Sursic galaxy model. And I've created three Sursic galaxy models here. And all three of them are going to interact with the point spread function differently. The first one, I set PSF convolve equals false. So even though our target, the target here, although it's a dummy target, we did give it the PSF model, that empirical PSF model that we had before. We gave it that PSF model to work with. So this target has a PSF model ready to go, and it could have convolved with this Sursic galaxy model. We set PSF convolve equals to false, and now this model in particular will not do any PSF convolution. You're going to get the Sursic exactly as it is projected right into your image. The next case, you set PSF convolve equals true. And actually, this is the default value. So if you just don't do anything, if you just get rid of that line, that's the same thing. But I'm adding it in here to be explicit for the sake of the tutorial. So PSF convolve is by default true. And that means that what AstroPhot is going to do is it's going to model the Sursic galaxy in the image. So it's going to do the integration of the Sursic galaxy into the image, and it's going to take their PSF model from the target, and it's going to convolve the two of them. It uses Fourier convolution, and then the model that actually ends up being in your model image, which then goes to your residuals and your likelihood, that is going to be blurred by this PSF model that you had in your target. The third case is, what if we wanted our model to have its own PSF model? Say we're concerned about the PSF changing across our image, and so not every model is going to be experiencing the same PSF. In which case, we can assign a new PSF. So here we create a new PSF image just by adding some perturbations to the old PSF model. And now we assign a PSF to this model here, and it's going to get its own PSF model that will be different from the others. So let's plot these model images. And once it's done that, you see with no PSF convolution, the Sursic has a really sharp peak in the center, and so it's very sharply defined, especially in the center, you can really tell. With the PSF convolution, we see that the whole thing is softer, it's more blurred out. The peak isn't as bright. You can see in the legend here, the peak is at 100 flux units in this case, whereas the peak for this one is at 10 flux units. Now, That doesn't mean that any flux has been lost. The two models should integrate to the same amount of flux, but the flux has been spread out more when the PSF convolution was done. And then this one has a PSF convolution, but it had its own PSF model. So even though these two are acting on the same target and the target has a PSF model that it was ready to give to every model, this one has its own special PSF and it does it its own way. Um, so now maybe that's not a realistic PSF, but I put it in there just to clearly show you that it is different. It's got that cross in it. Okay, now for the last little bit, upsampling your PSF model. So let's say that you're a little worried about the PSF model being too sharp for your pixels. Maybe your pixels are quite big and your PSF is undersampled. In fact, it's quite common to try and optimize your telescope design to be right at the edge of undersampling, to be at like Nyquist sampling, which is is pretty good for taking advantage of the resolution of your detector, but it means that your PSF model itself might be a little more blocky than it should be for really, really precise modeling. So let's take our PSF model or our PSF image. And this one, we're just going to create a really basic Gaussian. So it's going to be a nice, smooth Gaussian PSF. And we're going to tell it upsample 2. So that means that this PSF image, the pixels that it has, it's going to take 2 pixels to go across 1 pixel of the original image. This always has to be an integer, so you can do 2 times upsampling, 3 times upsampling. AstroPhot requires integer upsampling resolutions. It doesn't handle arbitrary upsamplings. And this is just for the sake of numerical efficiency. That way, AstroPhot can run all of its modeling at 2 times upsampling, and then at the very end, it just pools a set of 2 by 2 pixels, adds them together, and now boom, that's a pixel in your original image space that it can use to calculate residuals and a likelihood. So it's just numerically more efficient to do it this way. And um, now your PSF image is represented at 2 times resolution. AstroPhot will recognize that and trigger everything else to happen at 2 times resolution. So here you see we've updated the PSF for our target image. We just assigned it to that new PSF model. And now when we create a Sourcing model and we give it that target, you see we don't do anything else here to indicate that the model has been upsampled. But now all of the modeling will be done at higher resolution. Interest now, you keep in mind though that when you generate the model image, that model image is the model's projection into the target pixel space. So you're not going to get a model image out at 2 times resolution. You're going to get a model image out at the target resolution. It's just that internally, while the calculations were being done, it did those calculations at 2 times resolution and then pooled a 2 by 2 grid of pixels. Doing at least 2 times upsampling will make a noticeable difference in the precision of your photometry for things that have sharp features. Um, so it is recommended to do your modeling at higher resolution. If you only have an empirical model at the resolution of your telescope, then there's a few options that you have available to you. You could try and go get a new PSF model, maybe using something like PSFX or PIF, and these will let you model at higher resolution using cutouts from your image. So they still take target image sampling cutouts, but they try and model between the pixels and get you a higher resolution. Another option that's just faster to do is to take your empirical PSF model and use a detailed upsampling algorithm like Lanczos upsampling that does a good job of interpolating between the pixels, and then use that as your PSF model. Just working at the higher resolution is sometimes enough, even when the original model comes from uh, the data resolution. But the best thing to do is to try and model your PSF at that higher resolution using some other code or using some of the advanced features of AstroPhot, which we'll get into in a future tutorial. Okay, That's all we need to cover for this one. This is the basics of using your PSF models. You now know how to take your PSF model in whatever form you got it, put it into a PSF image, apply it to either a delta function point model in your image or an extended model in your image, and also how to handle upsampling so that you can model things at higher resolution and get more detail out of your fits. That's the basics of using PSF in AstroPhot. It's fairly object-oriented and I hope pretty intuitive, but of course, as always, contact me if you have more questions, and I hope to see you at the next video. Bye.